So what we actually have here, for a given C and D sequence, we actually have n separate inequalities here, where you can put in I is equal to 1 to n to get the n separate inequalities. Now we can modify all n of those inequalities by multiplying each one through by its relevant interval length. So for I is equal to 1, we'd multiply through by the length of the first subinterval. For I is equal to 2, we'd multiply through by the second subinterval's length, etc. all the way up to I is equal to n, where we multiply through by the length of the nth subinterval. And because all of those lengths are positive numbers, we're not going to have to worry about changing the sign of the inequality, so it's a perfectly valid move. So what that produces is what we've got down here, that for all I is equal to 1, 2, all the way up to n, the following inequality holds true. And all I've done is taken this and multiplied through by delta xi. So here is delta xi times, and then I've got the same thing from here. So the modulus of the function evaluated at ci minus the function evaluated at di. And that's going to now be less than or equal to delta xi times what we've got here, which is the supremum of the function minus the infimum of the function over the ith subinterval. So now, because this inequality holds true for I is equal to 1, 2, all the way up to n, we can actually sum over I is equal to 1 to n, both sides, and the inequality will still hold true. So that's because if all of these things for all I are less than or equal to all the things on this side, then if we add all of those ones together, the sum we're going to get is going to be less than or equal to the sum of all of these ones together. So that then yields this inequality. So it's the exact same thing, but now we've added in the summation sign. So we've got the sum from I is equal to 1 to n of delta xi times the modulus of the function at ci minus the function at di is less than or equal to the sum from I is equal to 1 to n of delta xi times the supremum of the function minus the infimum of the function over the ith subinterval. Now this thing here, hopefully you will recognise, and hopefully you also recognise this, but let's start with this one. This is equal to the upper Riemann sum of fg minus the lower Riemann sum of fg using that dissection. So it's just exactly this formula that we had here. Meanwhile, this thing that we've got here is what we defined, our new definition. So now what we can say is that these things that I defined are always guaranteed to be less than or equal to the difference between the upper and lower Riemann sums. And that's going to hold true no matter what C and D sequences you picked. As long as they obey these criterion, all the arguments that we've used are going to hold true. So now what I'm going to think about doing is putting every single one of these possible sums, the values that you can get, into a set altogether. Now there are absolutely loads of them because there's so many choices for these C and D sequences. Remember, if we just consider the C sequence for a moment, C1 is allowed to be anything inside that first subinterval, so there's an infinite number of choices for C1. For C2, again, it's allowed to be anything inside that second subinterval, so there's an infinite number of choices for it, etc., etc. So there are so many different choices for the C sequence of points. Then you've got equally as many choices for the D sequence of points. And I'm saying you need to pick any possible combination of them, and you need to put all of these possible sums that you could build out of any possible C sequence of points and any possible D sequence of points, and I want you to put every single one of them into a great big set. So that's what I've written here. These sums, sum from I is equal to 1 to n of delta xi times the modulus of the function evaluated at ci minus the function evaluated at di, and our criteria are just that the ci's and the di's must be in the correct subintervals. So ci must be in the ith subinterval and di must be in the ith subinterval. So you let it range over all possible choices of the C and D sequences of points and put every single one of these values into this set. Now, what can I say about this set? Well, I can say that for every single thing inside this set, this value, the upper Riemann sum minus the lower Riemann sum, is greater than or equal to it. because this inequality holds true for all possible C sequences of points and D sequences of points. So everything inside this set is going to be less than or equal to this value. Hence, this value is an upper bound for this set. Now, I want to show that it's actually more than just an upper bound. It is the least upper bound. It is the supremum of this set. So I've written this out in full here. So the supremum of this set, of all of these sum values, is equal to the difference between the upper and the lower Riemann sum. And this is actually the reason that I got interested in these sums in the first place, because of the fact that if you put every possible value that these sums can take on into a set and look at what the supremum of that value is, it's equal to this difference, and this difference is something that I'm very interested in. Now note, the dissection here is fixed. Now, you can of course construct such a set for any dissection, but in this line here, the dissection, we're imagining we've chosen our dissection and it's now fixed, and we're saying that if you look at what the difference between the upper and the lower Riemann sum for our function, given that fixed dissection, it is equal to the supremum of this great big set. And here we are not varying the dissection. The sums here are all over the same dissection. What we are varying is our choice of points from each of the subintervals that we are using in this sum here. So my next task then is to convince you that this is true, that this value truly is the supremum of this set. Now I've already convinced you that it is an upper bound for that set, but I need to prove that it's the least upper bound, so that there is no number that is smaller than it that is still an upper bound for this set. Now, how am I going to do that? Well, I've actually drawn a number line to illustrate my strategy here. So let's say this value in white here represents this number, the value of this supremum, or the hypothesized supremum of this set, so the upper Riemann sum minus the lower Riemann sum. If I could show that there are values inside this set that get indefinitely close to this value in white here from below, so these are them shown in red on the picture. So if I can show that there are values that get indefinitely close to this value in white from below, that would prove that this was the least upper bound, because there couldn't possibly be a smaller number that was still an upper bound, because if you had such a smaller value, say it was here where I'm holding the red pointer at the moment, then everything in the set would have to be less than or equal to that value. So they wouldn't be able to get to the right of that value. They'd all have to be to the left of it. They wouldn't be able to go to the right. In particular, that means they wouldn't be able to get indefinitely close to this value here, because they wouldn't be able to get beyond this value here. So they wouldn't be able to get any closer than that. So that's why if I can show that they get indefinitely close to this value from below, that will have proven that it is indeed the least upper bound, because there cannot possibly be a smaller value that is still an upper bound, otherwise they wouldn't be able to get indefinitely close to this value. So I want to convince you then that I can find things in this set that get indefinitely close to this value from below. So how do I formally do that? Well, I'll take an epsilon greater than 0, and I want to show that given a general epsilon greater than 0, I can find something in this set that is within that closeness of this value. And if I do that for a general epsilon, and my argument works for any epsilon greater than 0, then it will hold true for any epsilon greater than 0, and therefore I will have values that are getting indefinitely close to this value if it holds true for all epsilon greater than 0, because it will hold true for the really, really tiny ones as well. So if I think about what the difference then is between this value and one of these, well, these are always less than this, so they're always going to be to the left. So I can think about taking this value, the upper Riemann sum minus the lower Riemann sum, and then subtracting off one of these values, and I want to show that I can find a C and D sequence of points such that this difference is less than epsilon. So if I consider what this difference is, well, it's going to be helpful to actually write this out as a sum again. So we're returning back to writing it like this, and then we can combine the two sums together. So we'll get that this whole thing is the sum from I is equal to 1 to n of delta xi, which is factored out of both of them. And then we've got the bit from this, which is the supremum of the function over the ith subinterval minus the infimum of the function over the ith subinterval. And then we've got minus the bit from here, which is mod of the function evaluated at ci minus the function evaluated at di. Now remember, I am in control of my C sequence of points and my D sequence of points, and I'm trying to find such a C and D, or demonstrate to you that they exist, such that this thing is going to come out as less than epsilon. Now, what is hindering me going further forward is these modulus signs here. They are causing a problem. So I'm going to get rid of them, and this is the reason I'm going to be able to get rid of them. I'm going to say that I am going to pick the C points and the D points such that in any one of the subintervals, the C point for that subinterval, if you evaluate the function there, is always going to be greater than the D point, or the function evaluated at the D point. Remember, I'm in control of the C and D sequences, so I can pick them so that this is true. For instance, if I get it the wrong way round, if I pick, let's say, in the third subinterval such that D3, when you evaluate the function there, is actually bigger than the function evaluated at C3, I can just swap them round. I can say the point that was D3 will make that our C3 point now, and the point that was C3 will make that the D3 point. So we can just swap them round. I'm in control of them. I'm designing those sequences. So I'm going to say I'm going to pick the CI's and the DI's such that for every single one of the subintervals, if you look at what the function evaluated at CI is, it is bigger than or equal to the value of the function evaluated at the di. Hence, this thing is always going to be non-negative if I do that, and then I can get rid of the modulus signs, and that's going to massively help me. So written out, this is that assumption that I'm making, that I'm picking these CI's carefully such that the function evaluated at each of the CI's is greater than or equal to the function evaluated at the corresponding di. And that means now that I can get rid of those modulus signs, and I've replaced them, you can see, with curvy brackets here. And now I just want to multiply out those brackets, so we'll get a minus in front of this one, and then the minus will cancel here to give us a plus. So in this next step, I've made quite a few jumps. So I've actually split this great big sum into two parts. I've taken this bit and this bit, and I've made them into one sum. So we've got the sum from I is equal to 1 to m, we've still got the delta xi, and now we've got the supremum of the function over the ith subinterval minus the function evaluated at our ci point in the ith subinterval. So that's from this, this, and this. And now the other bit that remains is we've got plus the sum from I is equal to 1 to m, the delta xi remains there because that was, remember, multiplying everything. And now we've got the plus this bit, so the minus and the minus have cancelled to give us a plus, so we've got the function evaluated at the di point minus the infimum of the function in the ith subinterval. So this, what I've got here, I hope you'll agree, is equal to what I've got here. So I've copied this picture that we saw earlier down to here to try and give you some intuition behind what we've got here. So if we just look at one subinterval, so we're considering I is equal to 1 here, then of course we know what delta x1 is, but let's think about what this is. The supremum of the function over that first subinterval minus the value of the function at c1, and then what we've got over here is the function evaluated at d1 minus the infimum of the function over that first subinterval. Now firstly, my picture here is wrong because on this picture my c1 actually had a value that was less than the value that D1 was being mapped onto, and I said I'm picking my C and D sequences so that that's not the case. So the first thing I need to do here is swap them around. I'm going to make this number C1 and this number D1. And again to stress, I am allowed to do this because I have free choice over what points we're using in that C sequence and what points we're using in that D sequence. My task, remember, is just to find a C sequence and a D sequence for which this inequality works. So when I'm looking for them, I can make these modifications. If I have a C sequence and a D sequence where they don't obey this for every single one of the subintervals, I can just swap them round and I'll get new, slightly modified C and D sequences, and I can work with those new ones instead of the previous ones, and that's what I'm doing here. So you can now see that for my C1 point, the value of the function is bigger than the value of the function for the D1 point. So now let's have a look at what this is here firstly. So the supremum of the function over the first subinterval is this value here. We're then minusing or subtracting the value of the function at C1, which is down here. So that's going to give that value there, a positive number, and you're then going to multiply that by the length of this first subinterval. Meanwhile, over here, you've got the value of the function at D1, which is here, subtract the infimum of the function, which is down here. That's the infimum over this subinterval. So that again is going to be a positive number, and you're going to multiply that by another positive number, which is the length of this subinterval. And you're doing that sort of thing for every single one of the subintervals that the overall interval is divided into, and that's what is happening here. Now the crucial idea is that for each of the subintervals, I can actually make this and this indefinitely small, and that's because of the definition of the supremum and the infimum. So take, for example, on this picture, this first subinterval here, if I move C1 closer and closer here, in fact, indeed, this function actually does obtain its maximum, so I could actually make it equal to that value, you can see that I can make the difference between the supremum and the value of the function evaluated at C1 indefinitely small. And that has to be the case because if I couldn't get indefinitely close to this value, if there was some value that I couldn't get beyond in my quest to get as close as possible to this value, then that would be a better candidate for the upper bound or the least upper bound of the function over that first subinterval. So to help illustrate this, I've drawn this picture here. So this is representing the supremum of the function fg over the first subinterval on the real line. And it has to be the case that if you look at all the values that the function takes on over the first subinterval, that those values get indefinitely close to this value from below. Because if they didn't, if there was some closeness that they didn't get within, then you would be able to mark that on here, and then all the values of the function over that subinterval would be less than or equal to this value. And hence this would be an upper bound for that set, and hence this wouldn't be the least upper bound. So because of its definition as the least upper bound of the values of the function over that first subinterval, it means that there are values of the function that get indefinitely close to it over that interval. In particular, it means that given any epsilon greater than 0, you can find a C1 inside this first interval such that if you look at the value of the function at that point C1 and you take the difference between the supremum and that value, it is going to be less than epsilon. Now the same holds true for the infimum, or the mirror image holds true for the infimum, that if you look at the value that the function takes on over this interval and put all of those values into a set, the things in that set must get indefinitely close to the value of the infimum from above. And again, the reason is, if they didn't, then there would be some closeness that they didn't get within, and you could mark that point on, and then that point would be less than or equal to everything in the set. Hence, it would be a lower bound, and this would not be the greatest lower bound. So again, you get this inequality. Given any epsilon greater than 0, there must exist some point d1 in that first subinterval, such that if you look at the function evaluated at that point minus the infimum of the function over that first subinterval, then that difference is less than epsilon. Now these arguments don't just hold true for the first subinterval, they hold true for the second, third, all the way up to the nth subinterval. So for all of these subintervals, these things, this and this, can be made indefinitely small, and that's the reason that we can overall make this entire great big sum as small as we like. So remember, we're trying to make the entire thing less than epsilon, so we're now going to have to modify these things that we're putting here in order to make the whole thing come out less than epsilon. So these are actually the values that we're going to need to use. So what we are going to do is we are going to pick the C and D sequences of points very carefully so that these inequalities hold true, and of course this relationship that we had up here needs to hold true as well. So let's look at this one here. So we're going to pick the CI's so that if you look at in each of the subintervals, you look at the supremum of the function over that subinterval minus the value of the function evaluated at your c for that subinterval, that it's going to be less than epsilon over 2 times n. So n is a constant related to our dissection. It's how many subintervals you've cut the overall interval into. And then we've got delta xi here. So for each of the separate subintervals, you're going to actually have a slightly different value here. So for the first subinterval, you're going to have delta x1 here. For the second subinterval, you're going to have delta x2, all the way up to the nth subinterval where you'll have delta xn. And that's necessary so that we can cancel the delta x's here. Now note, all of this is a positive number here. So you're just taking the original epsilon that we had, dividing it by a positive number, so you'll still end up with a tiny little positive number that you're trying to make this thing less than. So for each of the subintervals from I is equal to 1 to n, you need to pick a ci such that this difference is less than the relevant amount here, where the relevant amount means that you've divided through by the correct subinterval's length here. Similarly, for picking the d sequences, again, or the d points in the d sequence, you're going to need to pick them so that this holds true, so that if you go to each one of the subintervals and you look at where the d point in that subinterval is being mapped onto, it's being mapped onto something less than or equal to where the c point for that subinterval is being mapped. And we're also going to pick them such that in each one of the subintervals, the place where the d point in the subinterval is being mapped onto minus the infimum of the function for that subinterval is going to be less than epsilon, again, over 2n times the length of that relevant subinterval. So for the first subinterval, you'll have delta x1 here, delta x2 for the second subinterval, all the way up to the nth subinterval, where you'll be dividing through by delta xn. It is possible to do that. As I say, you can get these differences indefinitely small by picking clever choices for C and D, so you can certainly get them smaller than these values. So if you pick your C points and your D points according to the specifications that I have laid out, and I hope you believe my explanation that it is always going to be possible to pick C and D points that obey all of those specifications, then this whole great big sum that we have here, we can make a conclusion about how big it's overall going to add up to, and that is that it's going to add up to something that is less than the sum from I is equal to 1 to n of delta xi times, and now we're using this inequality here because each of these things here is less than its respective size here. Then you can take the delta xi in each case and you can multiply through by it. It's a positive number, so it won't change the sign of the inequality, and then you'll end up with n separate inequalities. And then, of course, if you sum over I, the inequality will still hold true. So this great big sum is going to come out less than this great big sum here. And you can see, of course, the delta x i's here are going to cancel, and we're just going to end up with epsilon over 2n summed n times. So we'll end up with epsilon over 2 here. Meanwhile, this bit, we're going to use this inequality. Again, we're going to multiply both sides through by delta xi for each one of the inequalities from 1, 2, all the way up to n. That's a positive number, so it doesn't change the sign of the inequality. We'll then have those modified inequalities, and we're going to sum over I is equal to 1 to n, which again will preserve the inequality. So this thing is going to come out less than this thing. So this thing is less than this thing is less than this, so these two things summed together is less than these two things summed together. And again, looking at this one, you can see the delta xi's will cancel, so you'll just get epsilon over 2n summed n times, which will give us epsilon over 2. So overall, this is just epsilon over 2 plus epsilon over 2, which is epsilon. So overall then, by picking C and D points according to those specifications, you can make this sum less than epsilon. And remember, this sum was equal to this difference here. So you're able to make this difference less than epsilon, and we just took a general epsilon greater than 0, so this will work for any single one of them. Hence, by picking your C and D points carefully, you can make this difference indefinitely small. Hence, these things do get indefinitely close to this value from below. So overall, at the end of this part, we have shown that this value is the supremum of this set.